Hi everyone, this is Dr. Smith. I'd like to take you through the briefing discussion of infrared spectroscopy and how we will use that to help us elucidate organic molecules, structure of organic molecules. I've broken the presentation into 4 parts. The first part's going to just be an introduction to the technique. The second part will look at some specific examples of hydrocarbons. Third part we'll talk about carbonyls specifically, and the fourth part we'll actually work through some examples so I can show you how infrared works and how infrared will integrate into mass spec to give us some critical data that we need to be able to have access to. This screen is a copyright screen, just to remind you not to share materials with others, outside of the class. Okay, how does IR spectroscopy work? What does it do for us? IR spectroscopy can be used to determine the presence of organic functional groups within a molecule, but I want you to think more broadly of that. I want you to keep in mind that although we'll detect the presence of certain bonds, I want you to also be thinking about if we don't see indications of a different bond, that means we must not have that type of bond in our molecule. It may sound obvious at this point, but so for example, later on when we're looking at IR spectra, if we don't have an absorption in a range of about 1650 to 1800, it says that you do not have a carbonyl in your molecule. So what's not there, what's absent, is as important as what is indicated by the data, by the absorption. How does it work? Different bonds in different functional groups absorb electromagnetic radiation of IR frequencies range at different energy. So by us being able to shine light through a sample and seeing what light is absorbed, we can get an indication of what functional groups, what bonds that molecule must have, and that will allow us to eventually elucidate the entire structure. Here at the top of the slide is just an example of what an infrared spectrometer looks like. The lid is open on this one, and you can see where the sample goes in the sample compartment. There are cells available so that you can look at solids, at liquids and gases, and the way that this works is over here where the arrow is pointing. The light source is under that cover, and the light will come out and go through your sample compartment. Any light that emerges from your sample not being absorbed will be detected on the right hand side of this instrument. So if we move down to the bottom here and we look at this schematic, here you've got the IR source, the light source on the left, and in this case there's a reference path and a sample path, so like it's split into two paths. For us, let's just talk about the sample. The light travels through the sample. If your sample doesn't have any functional groups that will absorb that light, it passes right through and eventually gets to the detector. But if your sample has double bonds or something that absorbs the infrared light, some of that light will not pass through the sample, and therefore the detector doesn't see some of the wavelengths of light that the light source was putting out. So it knows that there's an absorption going on. Just to give you a reminder of the electromagnetic spectrum, here's the infrared region of the spectrum. To the right hand side is the radio wave region where we used to have discussions about NMR. A schematic to sort of make you come up with a visual understanding of what's happening. So imagine that this molecule of HCl is somewhat like two spheres, the atoms, and the bond is like a spring. And imagine the photon colliding with that bond, and the bond absorbing the energy, the kinetic energy of that photon, and it causes vibrations to happen. So imagine the bond lengthening as the spring stretches and then coming back together and stretching again and going back together. So the energy required for each type of bond is quantized. It's specific for that type of bond that you will see that creates that kind of motion. Different kinds of motions can be observed. There's stretching frequencies, there's bending frequencies. You don't need to know so much about this. I'm not so interested that you know this. However, one of the things that we need to understand from this is that there's a lot of different absorptions that will be happening for even for very simple molecules. So there's going to be lots of absorption in the spectra. A lot of it we're just going to have to ignore. So we're going to have to be very careful in how we analyze this so that we'll be able to do it efficiently. If you look at the top, these are two stretching frequencies. I just wanted to point out because it comes back into play a little bit later with different functional groups. Notice that this was with this methylene, you have the arrow here is to indicate a stretching, and the other arrow on the bottom hydrogen is also being stretched out. So in this case, this is referred to as a symmetrical stretch because both carbon-hydrogen bonds are elongating at the same time. Elongate, shorten, but they're synchronized. They're happening at the same time. Or if you look at the image on the right-hand side, this is an asymmetrical stretch where one of them is lengthening as the other one is shortening, and vice versa, back and forth and back and forth. So this is an asymmetrical stretch. These two stretches require slightly different frequencies for the absorption of light to cause it to happen, and therefore it can show up as multiple absorption bands. We'll see this specifically for NH2s a little bit later on. So here's an example of an infrared spectra. Just let me sort of take you through this so we understand what's going on. If we look at the x-axis, in this particular spectra, the x-axis goes from 600 to 4,000, so 600 on the right to 4,000 on the left. So the numbers increase to the left. The units for this is wave numbers, reciprocal centimeters. So wave number is a unit that was, it's a unit of frequency, and it was made up so that the numbers range, generally between 0 and 4,000, a comfortable area for people to use numbers rather than using exponents of wavelength and so on. So one of the things that we have to remember, I would like you to remember, is as wave number increases, this means that the frequency is increasing. You know that frequency is proportional to energy. So as the wave numbers increase, the amount of energy to stretch that particular bond increases. So for example, we would expect the stretching frequency of a carbon-carbon triple bond to be higher than the wave numbers for a carbon-carbon double bond. It would require more energy to stretch a triple bond than it would a double bond, and likewise more energy to stretch a double bond than a single bond. So you would expect the wave numbers to be higher for the double bond than for the single bond. Okay. Along the y-axis is percent transmittance. Goes from 100 on the top to 0. So at 100, if the percent transmittance is at 100, all of the light of that frequency is coming directly through the sample unabsorbed. It's coming in from the source, being detected at the other side. There's no missing light. What we're looking for is we'll start at 4,000 and we'll come along until we see one of these negative peaks. So this peak here that has a little arrow saying that this is an OH bond. This is an indication of an OH bond of, say, an alcohol. And notice how wide it is. So what we'll do is we'll come along, the light is being absorbed, we go right down to the bottom. Let me turn my cursor into a pen, and I can come right down to the bottom and make a mark. And now follow that down to the x-axis, and you'll see this little black mark. Someone's done this for us. This is an image from the textbook. And you'll notice that the minima, the bottom of that peak, is at 3460, where this black mark is. That is the range of an OH stretch. So that where the position of this along the x-axis tells us what kind of stretch we have. If you continue coming along, we'll talk about carbon-hydrogen stretching in a bit, but here at this approximately at 3,000, either side of 3,000 is where we'll see carbon-hydrogen stretching. And again, we'll talk about this in much more detail as we work along. If we keep going down to lower wave numbers, the next thing that we come to is this peak here, which I just circled. And this is an indication of a carbonyl. Carbonyls are usually strong absorptions. They're quite often the strongest. They come lowest in the spectra. And they range from about 1650 up to about 1800, depending on what type of compound has this carbonyl. Is it a ketone? Is it an ester? Is it a carboxylic acid? That will differ depending on what type of compound you have. So we'll talk about that in more detail as we work ourselves along. Notice I didn't talk about below 1600 in the previous slide, and the reason is the spectra can be broken up into two regions. The region on the left is the functional group region. This is where we need to get information from. So this is where we'll learn about a molecule being an alcohol, being an alkane, having a carbonyl, and such. Between 1600 wave numbers up to 4000 is an interesting region for us to learn about functional groups. From 1600 down, this is referred to as the fingerprint region. It's a more complicated region where things move around a lot depending on specific molecules. So each molecule has a very fingerprint-like pattern down in this region. We will not talk about this region because it's challenging to be able to interpret. So I'll point this out in the next slide, but then we won't talk about it and discuss it anymore. So for example, if I show you two isomers, in this case positional isomers, where we have alcohols, 2-pentanol, 3-pentanol on the bottom, and we compare the spectra, notice that from 1600 up is very similar, almost identical. Where if we look at 1600 down, there are some significant differences in the patterns that you see within the spectra. So, from a functional group standpoint, which is how we're going to use the spectra, this can be really quite useful. So, we're not going to discuss from 1600 down. I just wanted to bring back to your attention the cheat sheet that we'll be using within quizzes and exams. So this is the top part. Become familiar with it. Notice that on the top and the far left column it talks specifically about the bond. So here we're talking carbon hydrogen. Then it talks about the functional group. Then the next thing that's important, don't worry about the vibration type, but then the frequency. These numbers tell you the range where we would expect to see an absorption. The next slide just is the bottom half of that table that you'll be using regularly. So that's the end of the first part of the presentation. So please keep an eye out for part 2 of this presentation.